Our next speaker is Meer Ashwinkumar. He will tell us about integrable deformations of the Breitenlohner-Maison model from 4D Chern-Simons. Please, Meer.
So I'll describe integrable deformations of the Breitenlohner-Maison model from 4D Chern-Simons theory. And this is work in collaboration with Matthias Blau that you can find on the archive, and it was also recently published in JHAP. So the fundamental idea is that in certain sectors of gravitational theories, such as the simplest example of 4D GR, there is a stationary axisymmetric sector that is integrable in the sense of being described by an integrable sigma model, say with target space SL2R mod SO2. More generally, in high dimensions, you can have gravity, d-dimensional gravity, and you can study a sector with d-2 commuting killing symmetries, and you can also find integrable 2D sigma model description. So the distinctive feature of such models is that the coupling turns out to be worldsheet dependent. So why this description of the stationary axisymmetric sector of, say, 4D GR is interesting is because starting from this lax connection, you can generate solutions to Einstein's equations in the stationary axisymmetric sector. And this was developed by Belinsky and Zakharov. And in particular, you're really looking at black hole solutions, or in high dimensions, black ring or black Saturn solutions, whereby the generation of new solutions from, say, some seed solution can be understood as a kind of singular gauge transformation of the lax connection. So this is what the sigma model looks like. As I mentioned, you have a worldsheet dependent coupling. So that's rho over here. So here I will use rho and small z to denote worldsheet coordinates. So small z here is not a spectral parameter. And for 4DGR, here the field G parameterizes this coset SL2R mod SO2 target space. So SL2R here tells you about the shape of your metric in the directions that you reduced. And SO2, the modding by SO2 just represents the freedom of changing your frame. Of course, in the reduction, there are some other fields as well. You have some Kaluza-Klein gauge fields, you have some scalar fields, which is a dilaton, you have 2D gravity, but locally, what matters is really the solution to G. This is going to tell you about your black hole solutions. So this is a very interesting integrable sigma model in relation to gravity. And in a very beautiful work by Cole and Weck from a few years ago, this model was derived from four-dimensional Chern-Simons theory. And this was also based off some previous work by Robert Penna, where the same model was derived from 6D Chern-Simons theory on twistor space. More recently, in the work of Cesaro and David Austin, integrable deformations of this Breitenlohner-Maison model were derived. And this includes Yang-Baxter deformations, both homogeneous and inhomogeneous, as well as auxiliary field deformations. So this is very interesting because it suggests that these integrable deformations could be understood as some kind of reduction of some kind of deformation of general relativity that somehow still has black hole solutions in them. And we could use integrability to understand these black hole solutions. In particular, these IFTs with worldsheet dependent couplings and parameters, these were previously also studied by Ben, Nat, and Arkady in very nice work where connections to one loop RG flow of these integrable field theories was shown. So the goal is to derive the integrable deformations of this BM model both homogeneous and inhomogeneous Yang-Baxter type from 4D Chern-Simons theory. As we shall see, we find a very nice match to the results of Cesaro and Austin. And I would like to point out that what is useful about the 4D Chern-Simons approach is really with regard to organizing and unifying the derivation of these sigma models. The lax operator comes for free as the solution for your classical gauge field in 4D Chern-Simons theory. So the techniques that I will show you will eventually allow us to derive more integrable deformations of the BM model in the future. So before I proceed, I will just very quickly review some basic facts about 4D Chern-Simons theory. I won't go too much in depth into the review since many of these things are familiar. But as we know, we have this four-dimensional Chern-Simons action defined by the Chern-Simons 3 form wedged with the meromorphic 1 form associated with the Riemann surface C. So in general, the meromorphic 1 form, it has zeros and poles, and the number of zeros and poles satisfies the Riemann-Roch equation. So at the zeros, we have disorder defects, singular gauge field configurations that ensure that the action is finite. In addition, at the poles of the meromorphic 1 form, we must impose appropriate boundary conditions. So typically, boundary conditions give us integrable sigma models, while branch cuts, as shown by Costello and Yamazaki, give us typically coset sigma models. So this is a nice way to visualize it. So here, these disks you can think of as poles, as being at the locations of poles. So in the work of Del Duque et al., these are called islands. So you can have multiple poles for your meromorphic 1 form. And at each of these poles, you have edge modes. So these edge modes are your fields of your integrable sigma model. While at these red dots you see here, these are representing the zeros of the meromorphic 1 form where the gauge fields have some singular behavior. So for the PCM, you have a single double pole and 2 zeros. At the zeros, of course, you have some singular gauge field behavior, while at the pole, you impose a Dirichlet boundary condition. And then you can derive from the 4D Chern-Simons theory precisely the principal cardinal model action. So the best known, perhaps, deformation of this would be the Yang-Baxter sigma model. So this was shown by Del Duque et al. And for example, the inhomogeneous Yang-Baxter case corresponds to deforming the double pole we saw on the previous slide to 2 simple poles. So now your meromorphic 1 form looks like this. It has 2 zeros and 2 simple poles. And the boundary condition imposed now is a non-local one. The boundary field space, because there are 2 copies of the gauge field at the 2 poles, the boundary field space is either G sum G or GC. So the boundary condition we impose corresponds to a certain isotropic subalgebra of this double. And it's specified by some solution, a skew-symmetric solution of the modified classical Yang-Baxter equation. Of course, there are 2 simple poles. That means there are 2 edge modes, but there is some gauge redundancy. There is a gauge redundancy that we fix that leaves us with a single edge mode that corresponds to the field of the Yang-Baxter sigma model. And for the homogeneous Yang-Baxter case, we use the same meromorphic 1 form as the PCM, but now the boundary condition itself is deformed. And here, the boundary condition is sort of a mixed Dirichlet-Neumann boundary condition, which involves a skew-symmetric solution of the ordinary classical Yang-Baxter equation. And this boundary condition can also be thought of as specifying some isotropic subalgebra, now of the boundary field space, which is described by the Lie algebra of the tangent bundle group. So again, we need to fix some gauge symmetry, and we are left with a single field, which is the field of the homogeneous Yang-Baxter sigma model. So in the work of Cole and Weck, they derived the BM model that I described earlier, as well as the higher rank analogs. So here I will use C and C bar, complex worldsheet coordinates. And capital Z is the holomorphic coordinate on CP1. A is, of course, the gauge field, but we also specify a Z2 automorphism of G. I'll describe in the next slide. But the main point here is that the meromorphic one form now has components in the worldsheet directions as well. So usually you only have DZ, but now you also have DXC and DXC bar. And moreover, here you find explicit worldsheet dependence in the Z component. So this is, of course, work of Cole and Weck, but this is our starting point for deformations of the BM model as well. The point here is that, as I mentioned earlier, for cosette sigma models, you need a branch cut. So we also want to study cosette sigma models, but here the branch cut turns out to be a worldsheet dependent branch cut. So to be a bit more technical, you have a worldsheet dependent Joukowski transform. And basically, you can think of the meromorphic one form we saw on the previous slide as being equals to dW, where W is related to the capital Z coordinate in this manner. So Z is a double cover of W. The Z plane is a double cover of the W plane. Mapping Z to -1 over Z preserves W. But that means we need to place a condition relating the gauge field on the two sheets. And this turns out to be involving a Z2 automorphism that we call eta. So for example, for SL2R, eta is chosen such that the invariant subalgebra is SO2. And this is what leads us to the SL2R mod SO2 target space for the sigma model. This is, of course, in the work of Cole and Weck, this involved imposing the Dirichlet boundary conditions at Z equals to 0 and Z equals to infinity. And you can then obtain the BM model and its various higher rank generalizations. And yeah, this is, of course, the familiar action, which we saw earlier as well. And so I will describe the inhomogeneous Yang-Baxter and homogeneous Yang-Baxter deformations from 4D Chern-Simons theory. So as I mentioned, here there is a branch cut defect that is worldsheet dependent. So now when we deform the boundary conditions, there should be some worldsheet dependence in these boundary conditions. So to be precise, for the inhomogeneous case, we deform the meromorphic one form. And of course, as before, the boundary condition will involve solutions of the modified classical Yang-Baxter equation. But crucially, the worldsheet dependence, crucially, there is worldsheet dependence in the positions of the simple poles of the meromorphic one form. Whereas in the homogeneous case, once again, we have mixed Dirichlet-Neumann boundary conditions. But now, instead of a constant parameter eta, we have the worldsheet coordinate rho appearing explicitly in the boundary condition. So we can show, using some arguments starting from the twistor space origin of 4D Chern-Simons theory, that the most general choice for omega would involve some function of the coordinate w. So we take this simple choice of omega being dw over 1 minus cw. That means there's a simple pole. On the z plane, this translates to 4 simple poles at 0, infinity, z plus, and z minus. Z plus and z minus are worldsheet dependent. And the residues match nicely, as you can see here. This is basically necessary to impose the usual non-local boundary condition to get the Yang-Baxter sigma model. And when we take C going to 0, we find that the simple poles approach 0 and infinity, respectively. So we recover the undeformed case of Cole and Weck. So a bit more explicitly, the Z component of the meromorphic one form looks like this. And it has these 4 simple poles, as I mentioned, and Z plus and Z minus have this rather complicated form. The crucial point is that the simple poles, as I mentioned, are worldsheet dependent. And as in the usual Yang-Baxter sigma model, you can also think of the boundary conditions as specifying certain isotropic subalgebras of the boundary field space. But now the equivariance condition forces the solutions of the classical Yang-Baxter equations at the two simple poles to be related via conjugation as such. So as I mentioned, the C to 0 limit recovers the setup of Cole and Weck, and in particular, the boundary conditions approach the Dirichlet boundary conditions of Cole and Weck. And this is the answer we get from 4D Chern-Simons theory. Here, I can show you that the coupling and the deformation parameter correspond to the simple pole, Z minus, which, as I mentioned, is worldsheet dependent. And in particular, we match a property that was found by Cesaro and Austin, that is, the coupling and the deformation parameter are proportional to one another. And also, we managed to derive the lax operator that matches the form found by Cesaro and Austin. Yeah. So for the homogeneous case, I can start on the W plane and impose the usual mixed boundary condition at infinity on the W plane. This translates on the Z plane to boundary conditions that have explicit rho dependence that you see over here. And this distinguishes these boundary conditions from the ordinary homogeneous Yang-Baxter case. And once again, the boundary conditions correspond to some isotropic subalgebras of TG, with the two R matrices being related via conjugation by eta. And the action that we find takes this form. And as before, we find that the coupling and the deformation parameter are proportional to one another. But here, it's just rho. Previously, we had Z minus. We also obtain the lax operator, which matches the form of Cesaro and Austin. So once again, we find agreement with the work of Cesaro and Austin. So just to summarize, we derived both the homogeneous and inhomogeneous Yang-Baxter deformations of the BM model using the techniques of 4D Chern-Simons theory. In the inhomogeneous case, as I mentioned, the locations of the simple poles are worldsheet dependent. In the homogeneous case, the boundary conditions have explicit worldsheet dependence. But the crucial point is worldsheet dependence enters the boundary conditions. So, of course, the boundary conditions correspond to isotropic subalgebras of the boundary field space. And we find that the 4D Chern-Simons theory gives us the lax operator as part of the derivation. And the nice thing is that these techniques can then be generalized to many other models in the future, hopefully, such as gravitational analogs of the lambda model and E model. In the work of Cole and Weck, the origin from twistor space was also emphasized. So I imagine that these models can also be embedded in 6D Chern-Simons theory on twistor space. The 4D Chern-Simons perspective is also useful for the derivation of various dualities, such as bosonization dualities, as well as dualities like Poisson-Lee duality. I shall also mention some very interesting recent work on time-dependent integrability by Komatsu, Sakamoto, Wahlberg, and Yamazaki, where where connections to one-loop RG flow were also derived from 4D Chern-Simons theory. And the major question that remains is what is the gravitational interpretation of these deformed BM models? So that would be very interesting to understand. Perhaps this can arise from understanding the twistor space embedding a little better. So this remains to be done. So with that, I thank you very much for your attention.
Perfect on time. Thank you. Many questions?
Just in relation to the last question, I mean, what do the field equations look like? What does the lattice pair give you in terms of field equations on the sigma model G?
Sorry, the lax pair, the flatness of the lax pair corresponds to the equations of motion of the sigma model, of the deformed sigma model, as usual.
But what does it look like?
Okay. Okay. Yeah. So for homogeneous, this is the lax operator.
I see. But you don't have the actual equations for us.
Yeah, I didn't write down the equations of motion in these slides. Yeah. Yeah.
But you can't recognize what it is. Yes, the gravitational.
Not yet. Yeah. Yeah. Hopefully, eventually. Yeah.
Yeah, it's a bit the same question. You have in mind some kind of modified gravity or some higher derivative corrections of gravity, or what type of modification could give rise to that?
Well, there are some Chern-Simons and some BF descriptions of gravity exist. My guess is some modification involving some operators. These are just guesses. I don't know yet. Yeah.
Thanks. Thanks for the nice talk. I had just a quick question on this homogeneous time-baxter deformation. So you for sure know that there's in the the homogeneous time-baxter deformation of PCM, you might have this on-shell equivalence to an undeformed yet twisted version. Do you have this as well for the world sheet dependent one?
Yes, probably. Yeah. Yeah, well, this remains to be derived. Yeah, as you know, I'm trying to understand these things. But my guess is probably yes, and probably I think the 4D Chern-Simons perspective will also help us understand this as well. Yeah. Yeah, my suspicion is it's going to be worldsheet dependent basically since everything else has been worldsheet dependent as well. Yeah.
Okay, I also had a small question. Are these, maybe more curiosity, has a Poisson bracket algebra been considered for these cases, even in 2D? And would you, I don't know, expect that this has this crazy twist function that depends on the worldsheet coordinates as well?
So I believe this is in David's paper that they have the Poisson bracket algebra. Yeah, it's non-ultra local is what I remember. The concrete form I don't remember. Yeah. Yeah.
Good. If there are no other questions, then we can get to the break. Thank you, Meer. Thank you.